All right, need to talk a little bit about a technique known as trig substitution. And this trig substitution for integrals. This allows us to do some other types of, I don't know, best way to call them, integrals that have the fractions in them. You know, we have, for example, 1 over 1 plus x squared dx. Hey, that's nice because that's tangent inverse. Similarly, we have 1 over the square root of 1 minus x squared dx. That's sine inverse. So those are really nice. Well, what if we have one that's kind of close to that, but not quite? Well, as you know, close doesn't count a lot of times. Yeah, sometimes those just don't happen to work. I mean, yeah, if that's 9 plus x squared, 1 over 9 plus x squared, we can, you know, there is a way of doing that one. But what if it's not quite that? For example, let me find here. Yeah, say if we had the square root, sorry, the integral of 1 over the top is x squared, and then the bottom is the square root of 9 minus x squared dx. I think this is one of the ones that we will do. Yeah. Well, that's, I guess if you looked at it, you might say, hey, that is related, okay, to that. However, the problem is what? The top's not a constant. The top is an x squared. And yeah, it just doesn't quite work out in utilizing this inverse sign because of that x squared on top. It just doesn't quite fit, okay? If it was 1 over 9 minus x squared, you know, we can use the sine inverse on that, but it's x squared. It's got a variable on top with it. So that's the kind of things you run into is those little extra pieces. And in this case, yeah, you just can't use sine inverse there. Now, there are some on this assignment where you can use a sine inverse. So you always want to, you know, be sure and check for sine inverse or tangent inverse. Those are the two main ones for the inverse trig there, because this trig substitution, it's a whole big production. Let's say there's a lot to it. Okay. All right. So we'll come back to that. The reason it's called so we're going to use trig substitution on this one. The reason it's called trig substitution is because we're going to substitute for x a trig function. Now let me just kind of show you some steps. We'll do this one here in a second, but let me just tell you about the trig substitutions first. Say I have x squared plus 9. X squared plus 9. And that's what I'm going to make my trig substitution on. Well, it turns out what I'm going to do is I'm going to substitute for x the value 3 tan theta. 3 tan theta. 3 tan theta. You might be thinking, why would you do that? Well, there are reasons. And it will, really what we're doing is we're trying to take this, which is 2 terms, and by doing these trig substitution, that becomes 1 term. It'll become 1 term, and you'll see how it is. So let's go ahead and do that just to show you how it works. So 3 tan theta goes in for x. right? So it'll be 3 tan theta squared. So that's going to be 9 tangent squared theta plus 9. Now you can kind of see why we did the 3, right? Because that will make it factorable. We can factor off the 9. To make it 9 parentheses tangent squared plus 1. All right, but then the beauty of this too is the reason we did tan theta is because now tangent squared plus 1, if you look at your trig identities, remember your trig identities, what is tangent squared plus 1? Secant squared. That's secant squared theta. So that was what we're trying to do. We went from 2 terms down to 1 term. Okay. Now, there's going to be a lot more to it, but that's the first step basics anyway. Okay. Now, here are the trig substitutions made. You can see here that that's where you want to do the tangent. You got a something squared plus another number. So here are the recommendations for the trig substitutions. Yeah, if you have x squared plus a squared, so number 1. If you have x squared plus a number squared, then let, or of course, vice versa, a squared plus x squared. Let x equal a tan theta. Just like we did there. All right, so here we've got what? X squared plus 3 squared. Up here we had x squared plus 3 squared. And so we let x be 3 tan theta. So it's going to work the same way if if you have the same similar setup. X squared plus a squared, let x equal a tan theta. All right, well, what else can happen? We can have a squared minus x squared. That's going to be our expression that we're going to trig substitute for. Well, in that case, we're going to let x equal a sine theta. A sine theta. And notice here I am changing variables. I'm going from x to theta, so that's a big deal. Be sure you note that. We are going to change all the x's over to thetas. And then change it back again. All right, then last but not least, this gets both of those, but x squared minus a squared is different. If you have x squared minus a squared, we're going to go the other way, go another way. X equals a secant theta. You got that. Okay. Now, if I let x equal one of these 3, well, for example, let's say I let x equals a tan theta. If I divide both sides by a, x over a equals tangent of theta. What that sets up is our fundamental triangle ratios, whatever you want to call them. So don't forget about those. What I can say, yeah, if I choose this one to be our theta angle, tangent being what's tangent as far as the relationship of the sides of that right triangle. Opposite over adjacent. Yeah, tangent is opposite over adjacent. So this is the opposite of theta, so that would be x. And then a is the adjacent, so that would be a right there. So that gives me those two sides, and then what about the third side? Well, the third side is just Pythagorean theorem, right? A squared plus b squared equals c squared. So wouldn't this side here, what would it have to be? Well, that's c, right? That's the hypotenuse side, so that c squared would equal
squared plus x squared.
a squared plus x squared, or x squared plus a squared. So c would be the square root of a squared plus x squared. So anyway, you know, of course it works a little differently, but you know, you can use the sine or secant, but we will use that sort of thing along the way too. Okay. With me so far? Okay. All right, well, let's try one. Okay. Like I said, these get quite involved. So let's see how one works. All right, so let's go back to that one I mentioned. X squared over the square root of 9 minus x squared dx. Well, so going by what we've been told, we already went through, can't use, it's not an inverse sine, unfortunately. However, looking here, which of these three do I have, do you see there that I might be able to do that trig substitution on? It's right here, isn't it? I've got the a squared minus x squared scenario, don't I? So if I'm going to use, so my trig substitution is going to be x equals a sine theta. What is the a here? Well, my a, this is 9, but that's a squared, yeah. So that's my a squared, so a would be 3, wouldn't it? So x equals 3 sine theta. Now, what else I need here? So this is trig substitution, not u substitution. But I still do need dx. So I got to do the dx thing here. So dx would be the derivative of this, which is 3 cosine theta times d theta. And that, since I'm replacing dx, that is dx. That's what I'm going to replace dx by. And then the other thing, or that's different from the way I do u substitution anyway, others do it differently, is, you know, if I was doing this u substitution, I would just substitute on this. I would leave that because that wasn't what I was substituting. But on trig substitution, you substitute for x everywhere. Wherever you see x, it's going to be 3 sine theta. So that's going to be 3 sine theta squared on top. So that's going to be 9. Let's go ahead. So these get long, so I'm going to save as many steps as I can. So that's going to be 9 sine squared theta, right? Divided by the square root of 9 minus 9 sine squared theta. And then dx, like I said, dx is just 3 cosine theta d theta. So far, not bad, right? You just have to, you know, that would be probably, you know, allow you to use a note card on the test. That little chart right there might be a good thing for your note card there. But all right, so yeah, I'm going to do the substitution there. And now there's a little bit of simplifying. Actually, this one simplifies down pretty nicely. We got 9 sine squared theta. All right, then, like we did with the tangent one over here, we got a factor of 9 here I can take out. Everything else kind of comes along. And, you know, I guess it's the first time through, kind of do it step by step. What is 1 minus sine squared equal to? Is that simplified down quite a bit? 1 minus sine squared is cosine squared, isn't it? So I'm getting somewhere here. I've got 9 sine squared theta divided by now, and that's kind of, I couldn't, you know, I can't split these up. I can't do square root of 9 minus square root of x squared. I can't do square root yet. But now it's just a single term. I can square root that. That's 3 cosine theta on in the denominator. With me there? So yeah, I just simplify, work on that denominator there, and like I said, I went step by step. May not need all those steps, but kind of see them there. Well, all right, it won't always happen like this, but doesn't that help us out quite a bit? Yeah, okay. 3 cosine theta cancels out. Now we just have the 9 sine squared theta. Theta. Well, all right, so we know a little something about that. All right? Yeah, that's, just do that via the double angle identity. We've got even powered sine, so that tells me to go into the double angle. So that'd be, where are you going to put the 9 there? Let's see, sine squared theta is 1/2 minus 1/2 cosine 2 theta. Maybe I should have taken it over here. I need a little more room to finish this off. It's one of those other whole board problems. We'll run into a few of those along the way here. You just copy there. So it's 9 times the integral of 1/2 minus 1/2 cosine 2 theta. Theta. Yeah, so that first part, that's going to be real easy. It's just going to be 1/2 theta. Let's do it this way, okay. But then I've got to deal with this minus 1/2 cosine 2 theta integral. But that's just a little u substitution, right? U is the 2 theta, and du is 2d theta, so d over 2, so I have 9 times 1/2 theta minus the integral of 1/2 cosine u and du over 2. Well, hey, that's just 1/4 sine of u, right? The antiderivative of the cosine. But again, let's save little steps here. U is 2 theta, so instead of rewriting that all that because of that, it's sine of u, but u is 2 theta, so let's go ahead and put the 2 theta back in there. And then we got, of course, the plus c. And let's go ahead and throw our 9 back in. So it'll be 9/2 theta minus 9/4 sine of 2 theta plus c. Okay, well, we've done the integral. The only problem is that's in theta. We started in x. And usually if they start with x, they want you to finish in x. So we have to, there's just a little more work after we actually get the integral done. Okay, now when we have this theta, what we did was we substituted x to be 3 sine theta. So we know something about sine theta, like I was saying on earlier. If I divide here by 3, I've got x over 3 equals my sine theta. Well, the problem over here is neither one of those is sine theta. That's sine 2 theta. We'll deal with that in just a second. Let's deal with this theta first. What am I going to get? Well, I can use this, though, to tell me about theta. If x over 3 is sine theta, then if I solve for theta, just a little kind of solving a trig equation type problem. Well, if x over 3 is sine theta, what would theta be? Sine inverse, right? Sine inverse both sides? Think of it that way. Sine inverse this side, sine inverse this side. Sine inverse of sine is just cancels out, basically, inverse. Yeah, theta is just the sine inverse of x over 3. Okay? Now, what do we do about that? I know sine theta is x over 3. Unfortunately, sine 2 theta is not 2 times x over 3. Doesn't quite work that way. Now, what you have to do is you have to pull out another trig identity. Again, it's on the sheet. And that is the double angle. We use the cosine double angle. Where was it? Right here. Yeah, right here. I use the cosine double angle identity. Well, here I need to use a sine double angle. And sine double angle, so sine of 2 theta, I've got it as x on the handout, but sine of 2x is 2 sine of x times cosine of x. So this is going to be minus 9/4 times 2 sine of theta cosine of theta. Plus c. The reason that's helpful is because don't I know what sine of theta is in terms of x? Yeah, that's what I defined, basically. Sine of theta is x over 3. The only problem is I also need to know what cosine of theta is in terms of x. And that's where you pull out the your trig triangle. I draw them like this, whatever orientation you want. But if I call this theta, sine's opposite over hypotenuse, so that would be x and that would be 3, right? Opposite over hypotenuse. And so on cosine, what do I need for cosine? Adjacent over hypotenuse. So I need that. Well, it's just a little Pythagorean theorem thing. That's our unknown side, so that's a, I guess, or b, or whatever you want to call it. A squared plus b squared. It'd be good to call it a, but you know what I mean. Let's call it b. So b squared plus x squared equals 3 squared. So b is going to be the square root of 9 minus x squared. So that's my adjacent. So putting those in, so I've got 9 halves times sine inverse of x over 3 minus the, let's see, we've got a little cancel there. So this will be minus 9 halves. Sine is x over 3. Cosine, like I said, cosine of theta is the adjacent over the hypotenuse. And so that's going to be the square root of 9 minus x squared over 3. So that's what I put in for cosine over here. The square root of 9 minus x squared over 3. Which actually works out nicely, doesn't it? Well, some of it. Yeah, that's 9 right there, so that's going to cancel the 9 out. So we just have, final answer, 9 halves, sine inverse of x over 3. Minus 1/2 x times square root of 9 minus x squared. Let's see. Whew, finally, huh? Yeah. Those are marathons, not sprints. Okay.